Hello everybody, Future Simon here, just jumping in before we get started with the video today to say that I run another channel called Explored, which is spelt XPLRD, because apparently I hate vowels. It's more of a documentary style video channel than you see on this channel, but if you dig this channel, you'll probably dig the videos over there as well, those weekly explorations. Get it? Explored. Whether it's looking at countries where insulting the king is a jailable crime to the use of diplomatic bags to smuggle cocaine, it covers a wide range of stuff. New videos on that channel once per week. Check it out through the link below and do consider subscribing. And into today's video. Hello everybody, welcome back to Side Project. Someone in the comments a while ago was, Simon, make a video about the world's most powerful engines. And I was like, well, that sounds a bit boring, but then I looked into it and I realized it would be fun. So that's what we're doing today. If you would like to suggest something, and this video is proof that I do look at your comments and I do make the suggestions, sometimes, if I like them, leave a suggestion below. If it gets lots of upvotes, quite frankly, I'm more likely to make it. So let's just dive in. Big engines. In everything from lawnmowers and fighter jets to cruise ships and school buses, engines of all shapes, sizes and designs provide power for a wide variety of applications. Some, like diesel engines, have been around since the late 19th century. Others, like jet engines, relative newcomers. Regardless of age, every class of engine is constantly being improved upon. In fact, some long-gone inventors would likely marvel at modern versions of their designs that are exponentially more powerful, reliable, and fuel efficient. And, well, they're also a lot bigger. Of course, the engines of the future are already under development in secure corporate research labs and development facilities and top-secret military installations in countries all over the world. But until those explode onto the scene, making this video terribly out of date, we'll have to satisfy ourselves with the following titans of power production. Do you like massive engines with impressive specifications? Then behold the Finnish Wartsila RT-flex96C diesel. That is a name. A turbocharged two-stroke behemoth that's been a mainstay of the global shipping industry for more than a decade. Though low-rev marine diesel engines like the Wartsila, I have no idea about the pronunciation, have traditionally had 12 cylinders, in recent years additional power was needed to cope with the weight of ever-growing container ships. So, more cylinders were added. The newest 14-cylinder version has been in service since mid-2006 when it made its debut on the Emma Maersk, a 1,300-foot container-carrying Leviathan with a gross weight of more than 170,000 tons. The engine displaces more than 25,000 litres and cranks out 110,000 horsepower and 5.6 million pound-feet of torque at slightly over 100 RPM. To put that in some perspective, because we're all like, that's big, the diesel engines in tractor trailers typically displace 15 litres and make a comparatively meager 450 horsepower. But as mind-boggling as its numbers are, the engine's sheer bulk is equally impressive. It stands nearly 45 feet tall, stretches almost 90 feet from end to end, and weighs more than 2,200 tons, making it the world's largest and most powerful reciprocating engine. The crankshaft alone weighs 300 tons, or about twice as much as a locomotive. It's not just mass and unbridled muscle that make the Wartsila a standout, though. It features a number of relatively new advancements, like a common rail fuel injection system that makes it surprisingly economical as well. In common rail diesels, the low-pressure pumps that traditionally pushed fuel to injectors have been replaced by high-pressure rails supplying solenoid valves. When operating in its most efficient mode, the engine only uses about 1,600 gallons of heavy fuel oil per hour. That makes it a miser by big ship standards, which is a huge selling point for cost-conscious owners who spend major portions of their annual revenue on pricey fuel. Sadly, there's no mention of cost anywhere, but as they say, if you have to ask. Like shipping companies, airlines are in constant need of more powerful engines, but without fuel efficiency to match, they're usually dead on arrival. According to data from the US DOT's Bureau of Transportation Statistics, domestic airlines spend between $2 and $5 billion per month on fuel obviously before coronavirus. For most, it equated to about 20% of their total operating expenses. So, when manufacturers develop new engines that promise to deliver both of the aforementioned attributes, well, that's music to the airline's ears. In recent years, a number of competitors have unveiled powerful new jet engines, but it's the General Electric GE9X that currently reigns as the world's most powerful. Featuring a 16-bladed composite fan with a diameter more than 11 feet, it's a monster designed for use on Boeing's next-generation 777X wide-bodied aircraft. The 777X will be used primarily on long-haul routes by global players like Emirates, British Airways, and American Airlines. Assuming, who knows with Corona. However, some sources claim it won't take its first commercial flight at least until 2022 due to COVID-19 related production delays and drawn-out FAA certification requirements that include thousands of hours of ground and flight testing. Tell you what, those might be drawn out, but I'm glad that the engine that keeps me in the sky goes through a lot of testing. I like that. Nonetheless, when it does hit the air with these new engines, it'll be the largest twin-engine aircraft ever built. At full tilt, each engine will produce nearly 135,000 pounds of thrust, 5% more than previous models, without a significant increase in size. GE claims that the engine will be 10% more fuel efficient too, thanks largely to more weight-saving carbon fiber and ceramic components and innovative manufacturing processes like 3D printing, which will help when production is finally ramped up to cover a backlog of more than 700 orders. Cost per unit? Well, as they say, no, we know this one, it's $40 million, depending on how many you buy. They are bulk discounts, so if you need a lot, it's going to be cheaper. You probably need more than one. Though NASA's space shuttles are officially retired, when operational, they featured some of the world's most powerful engines. As semi-reusable low-Earth orbiters, they served between the early 1980s and 2011 as part of the agency's space transportation program. Most of us equate the shuttles with the recognizable craft that resemble conventional airplanes, but they were just one of the many components, including 3 main engines, an external solid fuel tank, and 2 rocket boosters. The boosters were responsible for lifting the shuttle off the pad and pushing it to 3,000 miles per hour, after which they were jettisoned to save weight. From there, orbit was attained under propulsion from the 3 main engines, each of which produced a whopping 400,000 pounds of thrust, or 3.5 times as much as the aforementioned GE9X. Together, they generated 1.2 million pounds of thrust, enough to push the 4.4 million pound craft to more than 17,000 miles per hour. The powered portion of the shuttle's flight lasts less than 9 minutes. Designers succeeded in producing a previously unattainable thrust-to-weight ratio by increasing the pressure under which the fuel was pumped into the combustion chamber, but as you would expect, consumption was unfathomably high. The main engines were among the most complex ever built, but despite internal temperatures that often reached 6,000 degrees Fahrenheit, they served faithfully for more than 2 decades. In fact, engine issues never resulted in a delayed launch, and unlike the predecessors, they could be used multiple times. From its inception in the early 1970s, the program was billed as an epic leap forward in space exploration, and it was even suggested that flights would eventually occur as frequently as once a week and at a cost of only $20 million a pop. But in reality, they were much fewer and farther between and, well, a lot more expensive. Total program cost came in at a staggering $220 billion, with a per-flight cost pegged at $1.5 billion, or 75 times greater than the original projection. The numbers prompted many detractors to ask whether it was worth it, especially considering that of more than 130 flights, 2 ended in tragedy, taking the lives of 14 astronauts. Now the retired space shuttles Atlantis, Discovery, Enterprise, and Endeavour are spread far and wide, from Florida to California, on display for all to see. Not ones to rest on their laurels, despite previously building a supercar capable of hitting 280 miles per hour, premium Swedish auto manufacturer Koenigsegg recently set out to make an even faster car, the Jesko. Though the Jesko's engine doesn't technically rank as one of the world's most powerful based on raw might alone, compared to piston engines in other limited production cars, it's a world beater. Produced in a country more known for blondes, IKEA, and a 6-hour workday than high-dollar speedsters, the Jesko's state-of-the-art power plant propels the 3,100-pound wonder car to such amazing speeds that it's a member of an exclusive club of automobiles called hypercars. The power comes from a 5-litre twin-turbo V8 that revs all the way up to 8,500 RPM, generating nearly 1,300 horsepower and 1,100 pound-feet of torque. It also features a unique flex fuel system that allows it to run on regular high-octane gasoline or E85 ethanol, the latter of which is a great option for those who need another 300 horsepower because, well, why wouldn't you? The engine also sports pistons with curved ceramic faces that increase compression, reduce weight, and prevent dangerous hotspots from forming when it's running wide open. To get all of that muscle to the road, Koenigsegg engineers opted for an innovative 9-speed transmission featuring a multi-clutch design that shortens shift times down to fractions of a second. The Jesko is available in a street-legal base model and a track-only version, and they both come with 4-wheel steering that improves cornering and steering feel. But all of that power and handling are worthless if the car can't stay on the road when it gets up to speed. To make sure that it does, designers improved downforce significantly over the previous models. At 150 miles per hour, it's nearly equal to the car's weight, which drivers claim it makes it feel like it's cornering on rails. The car is capable of reaching 300 miles per hour and rocketing from 0 to 60 in 2.5 seconds, only a few tenths of a second slower than a Formula One car. Of course, when talking about fast cars and powerful engines, there's never any shortage of controversy. What constitutes a production car is debatable, and what is street legal and where. There's also an interesting cross-Atlantic rivalry heating up that's pitting American manufacturers against those in Sweden, Britain, Italy, and Germany. But regardless of where they're made, hypercars are now reaching previously unimaginable speeds consistently, and some with electric and hybrid engines have even more horsepower than Jesko's V8. Not that it matters to most of us. With a production run of just 12, each Jesko is going to go for a cool $3 million, making them the exclusive playthings of the uber wealthy. When it was officially commissioned a few years ago, the USS Gerald R Ford ushered in a new class of aircraft carriers that gave the US Navy undreamed of capabilities. Displacing 100,000 tons and powered by 2 Bechtel A-1B nuclear reactors, the massive supercarrier slid into the water from its construction berth in Newport News, Virginia in 2017, ending the dominance of the Nimitz-class carriers that had served the Navy for nearly half a century. The Ford was constructed from more than 4 million pounds of metal, is coated with hundreds of thousands of gallons of paint, and is crisscrossed with untold miles of wires, pipes, and fiber optic cables. Central to the new ship's potency and durability are its upgraded A-1B reactors, which are smaller, more powerful, and more reliable than their predecessors. If the projections are true, they'll generate 125 megawatts of electricity and 350,000 shaft horsepower distributed equally between 4 propellers. Each day, the reactors will provide the power necessary to produce nearly 500,000 gallons of fresh water and 15,000 meals, but by some estimations, it'll take another 4 years and $750 million to get the $13 billion ship ready for active service because, like most mega projects, it was plagued by delays and cost overruns. Many were directly attributable to its new systems and lengthy sea trials, which are the only way to iron them out. Though exact figures for power and performance remain classified, it's thought that the combination of the most powerful engines and improved hull design will allow the Ford to reach 30 knots, or about 35 miles per hour. Since nuclear reactors don't burn fossil fuel for propulsion, the Ford will theoretically be able to operate continually for nearly a quarter of a century before it needs its tanks to be topped off. Other innovations include a redesigned flight deck, a new system for catapult-assisted takeoffs using induction motors instead of steam, improved surface-to-air missiles, and Mark 15 20mm cannons capable of spewing 4,500 rounds per minute at anti-ship missiles and aircraft that manage to slip through the carrier's outer defenses. The Ford will carry about 75 warplanes of all shapes and sizes and more than 4,000 service members, including sailors, pilots, officers, and Marines. So I really hope you found that video interesting. If you did, smash that like button below. Do not forget to subscribe. 3 videos a week on side projects, so you know what to do. As I said at the beginning, if you got a suggestion, hit me up in the comments below. I make the more popular ones. So go ahead and do that, and thank you for watching.